So this is the second video for section 10A, and this is one where I'm going to show you how to solve the questions. Now, this is the one point where I am going to recommend you do this differently from the textbook. The textbook uses these things called cast diagrams, which work like this: C-A-S-T, and this is 0 degrees here, and we rotate this way around. So this is 0 degrees, 90 degrees, 180 degrees, sorry, and 270 degrees. And these just tell you which things are positive. So A stands for all, C stands for cos, S stands for sine, T stands for tan. So between 0 and 90 degrees, sine, cos and tan are all positive. Between 90 and 180 degrees, sine is positive and the rest are negative. Between 180 and 270 degrees, tan is positive and the rest are negative. Between 270 and 360 degrees, cosine is positive and the rest are negative. Now, a lot of people feel those cast diagrams are useful and they think that they're a shortcut. Personally, I find them a little bit tricky to get my head around in the first place. And I feel like, well, we can use them, but if we do use them, we're still going to have to learn to use the graphs. Now, if we just learn to draw the graphs quickly and we look at the graphs, we can use the graphs to do everything that a cast diagram would do for us, and we don't have to learn to use cast diagrams. So I'm showing you what it is briefly, and I'm now going to do the rest of the chapter ignoring cast diagrams and doing it by a method of using the graphs. Now, what I should do here is I'll go through the exercise 10A, and I'll do a couple of bits from each question, which will be equivalent to the examples in the book, but I'll show you these without needing a cast diagram. So question 1 and 2, in fact, are both just practice for using cast diagrams, really. We don't need to do these if we're using my method, but they're not very difficult to do. So if we wanted to do them, draw diagrams to show the following angles, marking the acute angle that OP makes with the x-axis. So if it's a minus 80 degree angle, well, we start here. Positive direction is anti-clockwise, so a minus 80 degree angle is this way, so 80 degrees. 100 degree angle would be, a positive 100 degrees would be around this way, so that would be 100 degrees. It's 10 degrees bigger than 90 degrees, so this angle here would be 80 degrees because it asks us to mark in the acute angle with the x-axis. We can do that. We don't need to really practice that if we're not using cast diagrams, but there it is. State the quadrant OP lies in and the angle it makes. Well, you know, we labelled these C, A, S and T, so we can say which quadrant it is, and sometimes people label these as 1, 2, 3 and 4, but it's you know, it's a bit more practicing with these things. Now, number 3, for these ones, what I suggest you do for question 3 is start with a nice sine graph. Sorry, that's not a very good one, because we'll need to put the y-axis in the middle. Start with a sine graph, starts at 0 and goes like this, and then label it up 0, 90 and so on, and then do the same, get yourself a cos graph and label it up 0, minus 90, 90 and so on, and a tan graph. So we'd just deal with them like this. Look, sine of minus 90, well, minus 90 is here, so sine of minus, so this is sine, this is cos, sine of minus 90 is minus 1. Sine of 450, well, that's 90, 180, 270, 360, 360 plus 90 is 450, so 450 is here, so sine of 450 is 1. You'll notice that all of the numbers in question 3 are multiples of 90. Something interesting happens every multiple of 90 on a sine graph or a cos graph. Either you get to the top, you get to the bottom, or you cross the x-axis. Same with the tan graph, either you hit the x-axis or you have an asymptote every 90 degrees. So that's how we do question 3. Not particularly exciting, but it's pretty simple if you just draw yourself 3 graphs. Now things get more interesting with question 4, 5 and 6, and they work like this. So now, the techniques, by the way, that we're going to do in question 4, 5 and 6, you might think, well, why are we doing this? Why is it useful? And it will become more apparent the more of the chapter you do. But this is a thing that we need to be able to do. We need to say sine of 240, express in terms of a trig ratio of an acute angle. Okay, so in other words, sine of 240 is the same as, or is nearly the same as, sine of an acute angle. So what's that acute angle, and what's the link? So it works like this. Without a cast diagram, it works like this. We say this goes from 0 to 90 to 180 to 270 to 360. And we're looking at sine of 240 degrees. So 240 degrees is here, right? Between 180 and 270. So 270 would be the top of the curve. 240 degrees, well, that is 30 degrees away from 270. And if you like as well, it's 60 degrees away from the 180. And that's our number there, 240 degrees. Now we're going to use the fact that this area here is exactly the same as this area here, or this shape here is exactly the same as this shape here. This graph is completely symmetrical every way you want it to be. Each of these lumps is exactly the same size and shape. So if I look at 30 degrees away from the top and 60 degrees away from where I hit the axis, so we go 60 degrees in from here, 30 degrees in from there, then we get the angle 60 degrees, don't we? So from 0, 60 away from it is 60 degrees. From 90, 30 away from it is 60 degrees. And then if I go up to the graph and across. So this here is sine of 60 degrees, and this here is sine of 240 degrees. Okay? So what does that tell us? Well, this length here and this length here are exactly the same, because I've gone the same distance there and then up to the graph, the same distance there and up to the graph. Okay, that 30 degrees are the same. So if this distance is sine of 240 and this distance is sine of 60, that distance is the same as that distance. So we've just said that sine of 240 degrees is the same as minus sine of 60 degrees. They're the same size, but one's negative and one's positive. Okay, so that's the technique we're using, and we use that quite a lot. So let's just have another example. Cos of minus 50 degrees. This is perhaps labouring the point. If you understand this, then you don't need to follow this example through, but because it's a technique that we use so much, I'm just going to do it once again. Cos of minus 50 degrees, well, minus 50 degrees is here. That is 50 degrees away from the top, and it is 40 degrees away from the x-axis crossing point. If I get the same point in this part of the graph, the acute part of the graph, that is 50 degrees there. It's 50 degrees away from the top, it's 40 degrees away from the x-axis crossing point. So minus 50 degrees has got this cosine here. 50 degrees, if we go up to the graph and across, has got this cosine here. Sorry, my graph's a bit wonky, but you hopefully get the idea. So cos of minus 50 degrees is the same as cos of 50 degrees, because they're both positive and they're both the same height. Okay, so cos of minus 50 is cos of 50 degrees. Okay, and then 5 and 6 are really just variations on that. So sine of minus theta, it tells us here that theta is an acute angle. I'll do a couple from question 5 and question 6. Hopefully by the time you get there will make sense. I'll pick an example. They're all sines in question 5, just to make it nice for us. So here's my sine graph. Starts at 0, goes like this. Theta is an acute angle. What's sine of minus theta? So if I go minus theta this way and up to the graph, then that there is sine of minus theta. If I use the same trick, if I go theta degrees away from the point where the graph crosses the x-axis, that is theta degrees there, and up to the graph, and there is sine of theta. So sine of minus theta is the same as sine of theta, but negative. Okay, so sine of theta minus theta is minus sine of theta. And then question 6, you use the same sort of technique there. Okay, that's everything on section 10.1. It more or less solves 10.2 for you as well, but I'll do that in a separate video.